on demand, please go to our YouTube page. You can get there by searching in Google for Multifamily Upgrade on YouTube, or you can get a link there from our website, which is multifamilyupgrade.com. Today's presenter is Scott Blunk with Partner Energy, who's going to cover some of the nuances of the BPI Building Analyst Training course. To date, I'll also give you an update on our Tech Topic Training Series. We covered a series of tech topics in relation to Multifamily Energy Pro. We had 5 of these series on the topics that you can see on your screen. These are all completed, and these are also all available for on-demand viewing through our YouTube page. The rest of the BPI Training Series is going to last through July and into August. You'll see that on the screen today we're going to be talking about the next topic in our series, and that's going to be hosted today. In a couple weeks' time, we're going to host our last kind of topic area on building analyst, kind of the theory, and then in August, on August 5th, we're going to be hosting the building analyst assessment course. This will give you an idea of kind of the practical implications of some of the theory and content that we've been discussing so far. And then after the webinar training series are done, there is an opportunity to do some field training. There is a diagnostic training field day, which is available to all of you, and that's on August 20th at the Stockton Energy Training Center. You see the address on your screen here. That's an all-day course. It's available for you to get your hands dirty with some of the equipment and tools that you'll need to understand for combustion safety testing, and also just they have a great lab out there in the Stockton Energy Center to get familiar with different kinds of equipment, how to take them apart, how to identify some of their issues and related components. On the 21st, so the 20th is a Thursday and the 21st is a Friday, there's an opportunity for all of you to take a written exam. The written exam portion is 1/2 of the building analyst exam requirements that you'll have to meet. So in order to complete the building analyst certification, you'll also have to take a field exam, and the field exam is a arrangement that you'll have to make directly with Partner Energy or another field exam proctor organization. So more details are available if you contact me or contact Partner Energy directly. As you can see on the screen, the only fee that we're charging for is the fee for the written field exam. So if you'd like to challenge for the BPI Building Analyst test, the fee is $275 plus the registration fee for the actual test itself. And please enroll early. The space in the classroom is limited, so be aware of that. When you want to enroll, you'll have to pay your fee to reserve your spot, and there's an availability for 30 students to take the test on that day. With that said, I'm going to turn it over to Scott and mute my line so that we cut out this background noise. So go ahead and take it away, Scott.
Thanks, Mike. Hopefully they're not protesting you there in Oakland. It'll be much quieter here in Sacramento today. The analyst training, so just a refresher, this is an introductory training. It's not meant to give you everything you need, all the information you need. If you want to take the analyst exams, we suggest that you do further studying on your own. There's several good books out there. Mike has a flyer that he will send out to everyone who's registered for the courses that can give you a little more information on those 2 days in Stockton and on how to take your field exam and how to sign up for either one of those. So that should be coming. So make sure if you want to take the examination courses that you do study on your own. All right, so today we're going to be talking about furnaces, heating systems, and we're also going to talk about water heating at the end of this. All right, so just getting started here. And 3 main types of gas-fired furnaces. They're going to be a natural draft, which is a lower efficiency, an induced draft, which is middle efficiency, and condensing furnaces, which is the highest we can do in a gas system. So the lowest efficient furnace or heating sources out there that we typically see would be a wall furnace. I know this broadcast is going outside of California, so wall furnaces, I never saw one until I moved to California, but that's what they look like. You got a couple of the pictures on the next page. They're AFUE, annual fuel utilization efficiency is usually somewhere around 65%. When they're new, they don't get really much better than that. Most of the time they're naturally drafted, although I'll show you a picture later on of, well, they're always naturally drafted, but there's usually no other electrical, mechanical, or electrical systems inside. No fans or anything. This is just operates off of the fact that heat rises, so the heat comes over the heated plates inside the heat exchanger and heats the house, and then it keeps the hot gas away from the air inside the house and the hot gas, the exhaust vents out. So there's no fan used in this to help get the exhaust out, and that's really why the efficiency is so low. In these systems, they need a lot of heat in the exhaust, so that because heat rises, so if you keep a lot of heat in the exhaust, it rises better, and so it'll exhaust better. So if you got these any more efficient, then you would need to do something else to help get the combustion gases out of the unit or out of the home. And then the heat is just transferred by radiation and convection, essentially, in the home. Mostly convection. So like a ceiling fan or something would work well here to help spread the heat in the home. So a couple other pictures of natural draft furnaces. I grew up in Indiana, and I never saw one of these till I moved here. But if you pay attention to the Hollywood movies, you'll see these in the backgrounds. I later realized. But that's what it looks like. The picture here on the right, this is showing it without the cover on. It's natural draft, which means it takes outside air and mixes with the exhaust gases, and that's this box right here. And then it exhausts out the vent. And here in this, where it's installed, the vent pipe is inside the wall. So this is typically inside the wall. It's an oval shape, so it fits inside a 2x4 stud bay. And this is just, I guess, an artistic picture of the burner at the very bottom. That would be in this section here. So the burner's down here. This is the heat exchanger as it goes up. And then this adds dilution air to the exhaust just to help it draft out. So we're going to talk about some CAS stuff later, but if you're checking for spillage, it's really right around here that you would find spillage in these units. So forced air natural draft furnaces. So forced air means it's got a fan that's forcing air over the heat exchanger. So it's not a fan about the exhaust, it's a fan about the heat exchanger. So called a squirrel cage, and I'll have at least a diagram on the next slide, but there's a big, what they call a squirrel cage blower motor in here. This is kind of the area that the burners are going to be in. And then there's going to be a heat exchanger here where the heat rises up. And then this is where, again, you would check for spillage right around here, and to see if any of the exhaust gases, as they come up, they spill out. But this is where extra air is added to the exhaust, and then here's your exhaust system. The silver piece is a HVAC evaporator coil. So this is the condensate line off of it. But we're just talking about the furnace today. So forced air means it's a ducted system with a big blower down below. Natural draft means that the draft is just working off of gravity alone. with the way these, about the best you can get in terms of efficiency is about 75, 85, or 75 to 78%. Usually operating in about that range. It's part of a central ducted system, and there's no fan involved that helps the exhaust gases leave the exhaust pipe or flue. And then heat is entrained in the forced air distribution system, and I'll show that on the next slide a little bit. So these are just a few different pictures of kind of how it, to help explain how it works. So this is a side view of what we just saw. The blower motor's down here, so the return air comes in. This air never mixes with this. So this is the burning chamber or the heat exchanger. So the gas burners are here, and this is a picture of the gas burners here. So usually they shoot in, or they could be small flames here, but modern days they look more like a rocket engines here that they shoot flames inside. But either way, the combustion is happening here. The gas and combustion burners are here, and the combustion is happening here. The heat and the exhaust fumes and all the exhaust gases stay inside this chamber here, and it just goes back and forth until it goes out the flue, and this is where that dilution air is added. So I'm going to go back. So again, this is the dilution air being added. Here's the burners here. So inside is this serpentine that goes up to the exhaust. So that's what it would look like if you, in diagram form. So this air, the return air, so this is returning from the home. This air goes over the outside of this heat exchanger, and this is an example. It's a little bit different heat exchanger, but it's the same principle, where the burners are here, the flames are at the bottom, it goes up, and then it comes out the exhaust here. But the air, the house air inside, never touches or gets involved with the air or the gases inside the heat exchanger. So the two are kept separate in that manner. The reason why this is a serpentine, it goes back and forth, and here it kind of wiggles up. The reason why is just to increase surface area. The more surface area, the more heat you can get out of the system. There is a limit, like we spoke a couple slides ago. The more heat you take out, the more heat you take out of the exhaust and transferred to the air that's going back to the house. The principle that hot air rises, you're negatively impacting that by taking more heat out of this air, so it won't exhaust as well. So that's why usually you see a natural draft furnace topping out at around 78% efficient. They just haven't figured out how to make a natural draft work better than that, because you need that other 22% of heat in the exhaust gases to help it leave the house. So again, returning air from the house. The blower blows it across the heat exchanger, and then the air from the house gets supplied back to the house, and that's all usually ducted. There's always going to be some amount of duct work involved in these to keep them separate. So again, this is your heat exchanger, just a different version. Most of the time, and especially these old ones, are going to kind of rock back and forth like that. And then induced draft furnaces, this is kind of the minimum efficiency that anyone would install today in a system or in a house. They're usually around 80%. Again, they suffer from the same problem that you can't take too much heat out. It's called an induced draft, and this right here is a picture of the inducer motor. So your burners are here. There's the heat exchanger inside that operates just like the one I showed you, where it's going to serpentine back and forth until it's going to exit here or somewhere up here. So this is your exhaust collecting and going out. This it induces draft. It doesn't create a draft. That's why it's called an induced draft furnace. And what that means is that it just helps get the draft going. It does, but it doesn't. The fan isn't used to push gases out. So if you were to drill into this vent pipe and check the pressure inside the vent pipe would be negative, because it's operating off of hot air rising, and the negative pressure inside that pipe helps suck out the exhaust gases. So, and that's the same thing for what I've already shown you in the natural draft furnace and the wall furnaces. They all operate off of hot air rising, and that's meaning that inside this vent pipe there's going to be a negative pressure. What that allows is it allows this vent pipe, you don't need a perfect airtight seal on it, because if there's a small leak in this vent pipe, it's just going to suck fresh air in. Of course, you don't want too many holes, but small holes are fine, or just seams that aren't sealed perfectly, because the pressure inside is negative. So it's a fairly safe system, vent system anyway. Drafted into flue, so yeah. So again, you just can't take much more than 80% of the heat out of the combustion products here. So just to go over a little bit what some of the stuff is, this is the gas line coming into the unit. It comes in and across and comes back into this. This is a gas pressure regulator. This right here is the knob, where it's just like on your water heater, where you can turn the gas off. Of course, typically there's going to be there should be a valve on this pipe here somewhere, right before, maybe it's right up above the picture, where you can shut it off there as well. You're going to have that. A lot of electronic controls that are monitoring the gas pressure. The gas, once it leaves, it's fed down to these two burners. You could have 2, 3, 4. I don't think I typically see more than 4, but so this is a smaller furnace than a lot. This right here is a pressure. It's a device measuring pressure. Can't think of the term right now, but what it's measuring is making sure. Essentially, what it's doing is it's making sure that the fan is running by measuring pressure. Because if there's not a negative pressure in this pipe, it'll signal to shut the system off. I think that's about all we got there. There's another slide with a little more details about these furnaces. So again, this is what I was talking about, the fan limit switch, but basically it's just a pressure switch. There's usually, it's the same picture there as before, but usually there's not a wire, it would just be a small rubber hose that goes somewhere over here. I can't see it, maybe it's that black one, but it's just measuring pressure. So if you don't have a negative pressure, it'll shut the system off. 3 burner as opposed to here we've got 2. The gas valve again, the pilot, the ignition control. These on these newer units, most of the time it is it's a heating element that turns bright red. So when you would first turn on a furnace, if you're kind of geeky, I guess, like me, it's kind of fun to watch a few times to see it happen. But when you turn on the furnace, you'll look in here, and it's safe to do that with this. There's a door that goes here, but you can take that off with it still working. The blower motor's down here, that has to be on. But you open this door, turn it on, and you'll watch on these units, there's typically like a glow plug, just like it would be in a diesel engine where there's no spark plug. It's a glow plug. It'll start glowing bright red, and there's a temperature sensor next to it so that the computer knows it's ready, and then the gas is released, and the gas goes across that red hot element and ignites. And then they ignite, and then these three just shoot flames straight in like a torch or a jet engine. Like I said, I think it's kind of neat, and my kids liked it too. Fun for the whole family. So this is the fan. It's just it's a little different version, but it's essentially the same. And on this one here, when it's running, this will actually be turning, and you can see it. Sometimes it's a plastic cap kind of, and you can touch it, and you'll see that it's spinning. There's what else? The heat exchangers back in here, and this is the exhaust gases coming out here and going up. Just another switch to make sure that it's drafting properly. Here, on these systems, it's very hard to check for spillage. I've seen and heard a lot of people talk about different ways to do it, like through around these seams. It's not a very good check. Some people will check for spillage around here. That's another option. Never seen one spill from either one of those places, but you can do it. Inducer motor gas limit switch is there. Gas line is this one here, right? Igniter. I don't see the igniter here either. This is another flame rollout switch. That's this right here. Probably going a little fast today. Too much coffee. Burners, and then the blower motor is down here. That's induced draft furnaces. Like I said, if you're builders and building something today, this is typically what you see put in. It's the cheapest option and the lowest efficiency allowed. Natural draft furnaces aren't allowed to be installed any longer, at least in California. Condensing furnaces. So condensing furnaces or high efficiency furnaces are usually in the 90 to 98% efficient. And so really what that AFUE means, we call it an efficiency, but it's really an annual fuel utilization measurement, but it's essentially an efficiency. And it's telling you what percentage of the heat are you taking out of the combustion process. So here you're getting 98%, on this one, 98% of all the useful heat out. So you're losing 2% of the heat that would go out of the exhaust. And here the exhaust is probably this one, could be that one, probably this one. And you'll see that these are now white PVC pipe. And the reason why they're white PVC pipe here is because you have taken out all or so much of the heat that the exhaust gases are such a low temperature that you can just use the PVC pipe, the plastic pipe. And that makes the venting system cheaper. It's easier to work with. The parts are pretty readily available, so that reduces the price of that. The reason there's two of them here, it's good practice at least to have fresh air coming into one. Like I said, it's probably this one, the fresh air is coming in, and then the exhaust is going out. You could just have this open, and then it could be drawing air from this closet, but it's not recommended to install that way. And there's much less to see in these because the condensing furnaces are closed combustion, so the flames are all kind of sealed in. Next slide will show you some diagrams. So furnace down here, again, this is the AC coils up above, condensate line, the line set coming into the air conditioning, but we're talking about this box down here, the furnace right now. So yeah, exhaust gases are cool. You still want them to vent all the way outside the building shell. The exhaust is pressurized here. So before we talked about, on any of the previous ones we talked about, the pressure inside the pipe was negative. So it was naturally drafting, just based off of the heat in the combustion gases. It was drafting up out. Here there's very little heat in the exhaust gases, so there's a fan, one fan in here that does nothing other than to push the exhaust out. And then of course there's the standard, the typical fan in here that is blowing air. Air is coming in. This is the return register. Air is coming in and then blowing it across the heat exchanger. But there's a fan that all it does is pressurize the exhaust pipe to get it out. Yeah. Okay. And then, so some diagrams of condensing furnaces. Oh, and just condensing furnaces. So they're high efficiency, but they could also be called condensing furnaces, and that's because if you remember in the first presentation we talked about in the basics of building science, one of the products of combustion is water vapor. So because water vapor with dew point and all that stuff, the cooler air is, the less water it can hold. So you got your can of soda on your desk. The air right against that can of soda is cold, and that's condensing out the water from the air and sticking it on the side of your can. That's kind of what's happening in the exhaust system, where the exhaust gas temperature is dropping so low that the water condenses out of it, and then you have to have some place for that condensation to go. And in here, in this one, that's what it is, a condensate line to the drain. So it's different than your condensate line for your air conditioning. The water off your air conditioner is basically pretty pure water. It's just the water vapor in the air. Here, the water vapor is going to be mixed with some other pollutions from the combustion process, so it's acidic. And so when the water vapor does condense in, it usually runs across like a lime mixture that neutralizes the high acidic levels in that water, in that condensate water, before it goes out. So one of the other complexities of a condensing furnace is now you have to have a place to take the condensed water away. And like I said, after it runs through a lime or something that's going to neutralize the acidity in it, then the water can be released, and it's not harmful, but it's still going to go into the sewer system typically, or drift outside, I suppose. So again, this is the blower motor. This is the blower motor, the return. So that's the blower motor's down here. The air goes across the heat exchanger and then back to the house. In the combustion process, what's unique here is condensing furnaces. The heat exchanger operates backwards. So in everything I've showed you before, the burners are down low and the heat comes up through the heat exchanger and out the top. Here the burners are up high, and then they're forced to go downhill, and the heat's being eliminated or taken out of the exhaust gases all along the way until it gets to the bottom, and then the exhaust gases are the coolest down here. And so that's what the condensation is going to come down here. But the exhaust comes, the burners are at top, the exhaust comes out at bottom, and then it's going to exhaust out of the building. So here, same thing, the burners are up top. This is a more typical heat exchange pattern that you'll see where the heat exchangers, the flames are shot inside, the exhaust gases and the heat circulate down. It goes into a secondary heat exchanger, just a finer plate system. And then it's going to exhaust here. It's exhausting out right here at the side. And then the condensate is coming out as well. Burners are up here. Again, they're pretty. If you take this panel off, there's very little to see. You can no longer see the burners actually firing or anything. Okay. Other types of furnaces. So what I've shown you, other than the wall furnaces, have all been kind of from a split furnace. So split where the heater and the air handler are inside and the air conditioning condenser is outside. Well, that's what I've shown you. The other types of furnace are just a package system. That's just the metal box where it's going to have the air conditioning evaporator coil and condensing coil plus the furnace all in one box. That's what's going to sit on top of the house. Typically it's on top of the house. It could be on the ground beside it and feeding underneath the house into like a crawl space or a basement. But it's all the same thing is happening in a package system as what I've just shown you. There are some sealed combustion wall furnaces. They operate similar to the gravity wall furnaces, but they do have fans that help pull combustion air out and exhaust them. And then there's atmospherically vented furnaces where all the exhaust gases go straight into the living space. That's probably illegal in most states. I know it is in California, but they do exist. And why don't I pause here for questions, because from here we're going to go into a little bit of filters. So Mike, are there any questions?
Yes. So the first question is, how serious is the risk of CO poisoning associated with natural...
Can't hear you, Mike. Mike? We can't hear you.
How about now?
We got you now.
Okay, great. The first question is, how serious is the risk of CO poisoning associated with natural draft furnaces?
You know, it's not serious enough. If I had one in my house, I wouldn't take it out unless there was a problem with it. I wouldn't worry about it necessarily. They certainly are riskier than an induced draft or a condensing furnace. There's more risk associated with them, but they were out there for decades before induced draft started, and most of those people are still alive. Like I've seen them out there working for 30 years just fine.
Yeah, and I think there's a corollary to that question, which is about how is the venting set up. So if the venting is working fine, the natural draft furnace should be working fine too. So the dwelling unit in California, the reason these wall furnaces are so prevalent, or part of the reason that they are available to be put in, is our houses, our buildings are relatively drafty and designed to be that way, so to avoid moisture, but also because of the mild climate. So yeah, the seriousness of the CO poisoning, I think, is a number of factors, including how the system is vented and how the combustion is happening, not necessarily the fact of the design of itself.
Yeah, that's a great point, Mike. And
yep.
Let me just, that's a great point. And then what we see in these wall furnaces is that, you know, it could be there and it could be functioning just fine, but after you do, you air seal a house, it may not operate well anymore, because you do need you need makeup air and stuff that these old systems are assuming you have. So when you make homes more energy efficient, put new windows in, add insulation, do air sealing, you're typically make all natural draft appliances more risky. so you want to just, that's the reason why we do a test out on these as well. It's a good point, Mike.
Yeah, yeah, thanks for clarifying. So you need to be cognizant of all of the factors related to the CO poisoning issue. So as you tighten the envelope, that's going to affect how that, where that air is going and how much CO is being concentrated in it. There were some, just to let you know, Scott, there were some stuttering on a couple of the slides in the past. So I've gotten a couple comments from audience members that there was slides not advancing and pointers not able to be seen, and maybe some audio problems. If any of you have particular questions about any of the slides that seem to be stuttering or incomplete from your viewing of the webinar, please just ask, and Scott will go back and go over any of that information again. Next question is, can you recommend a textbook that a student can study for BPI Multifamily or for BPI Single Family?
Yeah, Residential Energy by John Krieger is kind of the main resource for BPI. I would say BPI in general, just for all the BPI certifications. It's not specific to multifamily. There may be a little bit in it. It's really geared towards single family, but all the principles transfer quite well. There's not a multifamily sort of textbook out there right now. Maybe that's my next project, but and yeah, I do the stuttering and the pointers and slides. Sorry, we're having a bad internet day here. No riots though.
Yeah, thankfully my riot quieted down too. I would just echo that Residential Energy, I'm looking at it right here on my desk. It's a great resource for doing the BPI analyst, and not all of the concepts are transferable, but at least the the theory is there, although the practicality will definitely change between multifamily and single family. There's a question, another question about gravity furnace. One of the audience members had an old gravity furnace, and is that the same as a natural draft furnace?
Well,
similar terms.
Yeah, a lot of times a gravity furnace, I guess, may depend on where you're at and just how the local people call it. But most of the time, a gravity furnace is going to be we would call it a gravity wall furnace or just a wall furnace, but it's but yes, they're typically natural draft.
Great, and those are all the questions for now. So I forgot to mention this earlier. Just want to let everybody on the call know you're all muted by default. So if you would like to ask a question or get in touch with us, please use the chat function or the question function. And at the end of the call, if there's anything that can't be answered by text, we can open up the lines and have any of you ask your questions directly or comments directly. So go ahead, Scott.
Okay. Filters. I know we touched on this the last section a little bit, but you were ahead of me apparently. And maybe next time I teach this, I'll put it in the other section. But Merv Filters, Merv minimum efficiency rating value. The higher the Merv, the more it filters out, and the more expensive. So just kind of some guidelines. The washable ones are pretty low Merv, so they don't wash out a lot of items. Pleated ones are kind of in the middle, and then the less electrostatic are the high Merv filters. And just a little bit better view of that chart. So just kind of conceptually gives you an idea of what can be filtered out with the different Merv ratings. So you know, anything from human hair down here, pretty much everything's going to catch that. And then moving up, these high Merv filters can even stop smoke and smog and bacteria. The problem, we spoke before, this is more of an issue with air conditioning than it is furnaces, but the higher the Merv, also the more it restricts airflow. The more you restrict airflow, the harder your fan is working. So the more energy you're going to use moving air in your house. So it's just something that you need to be aware of. You don't want to take a 40-year-old furnace and put in like the very best filter you can buy, because it wasn't designed for it. Merv didn't exist back then. So you want to replace your filter with kind of what was there already, primarily, unless you want to do some testing and make sure that you're not creating too much of a pressure drop across the filter, and just to make sure it's sized appropriately. Yeah. So there are other types of furnaces out there. We primarily, I showed you all gas fired furnaces. There's hydronic furnaces, which just there's hydronic furnaces, and they can be forced air or not forced air, but that's where they're using hot water essentially instead of burning a flame and running it in the heat exchanger. It just puts hot water through the heat exchanger and then blows air across it, or it could just not blow air across it. It could be just a radiator in the room, especially outside of California. That's a little more popular. So if you're going to have a hydronic system, you're usually going to have a higher capacity water heater, and so the water heater could be used also as the heating source for your furnace, or it could be two separate devices. So you could have a standalone water heater and a standalone boiler that would then heat the water for your hydronic system. There's heat pump and electric resistance. These are both electric heaters. Heat pumps are incredibly efficient, and of course there's no combustion products, there's no gas, so there's no fear of or danger associated with combustion products. Heat pumps are really a lot of building science people are pushing for heat pumps because they are so efficient, and they're just incredibly safe. They're price-wise, they're about the same as a gas furnace. The problem is, even though they could be, compared to gas, they could be 200% efficient, 250% efficient. They're still using electricity, which costs. It's like running your car on premium versus regular gas. Even though the premium is going to make your car perform better, it comes at a higher price. So electric heat pumps really are the way to go in terms of efficiency and safety. However, it's going to cost you more to operate them. So they're great to use when you've got solar on the house, or you just don't have access to gas, or just don't want combustion happening in or around your house. There's also electric resistance furnaces, and a lot of heat pumps have some electric resistance inside them too. And the electric resistance is just that they approach 100% efficiency. And we'll talk about that a little more in water heaters too, because there's electric resistance and electric heat pumps, water heaters. But you can heat your house this way too. So they're approaching 100% efficient, but even though they're 100% efficient, the cost of electricity is dramatically much more per unit of heat than gas. So gas is used because it's cheap to operate your house. Electric resistance around 100% efficient. Heat pumps around probably 250% efficient. They're not. It's a different type of efficiency, but relatively they're really super efficient. Heat pumps. The other thing you hear a lot is that heat pumps don't work well below freezing or at some temperatures, but I've seen a lot of different studies out there showing that heat pumps, even without electric resistance, can operate well into the teens. So it can be 10 degrees outside and a heat pump is still working, heating your house effectively. What heat pumps do, a heat pump is nothing more than an air conditioner that's working backwards. So it takes the heat out of the outside air and converts the heat from the outside air into heat inside your house. So it sounds a little strange that you could take 10-degree air from outside, pull the heat out of 10-degree air, and make your home comfortable at 70 degrees, but you can, and that's the way they work. But even in heat pumps in below 10 degrees or below zero, heat pumps have electric resistance backup. So if it really drops below temperature that the heat pump itself isn't working, the electric resistance will kick in and get you through that period. Of course, that's more expensive, but even in most places in the United States, it's not going to be below 10 for too long a time. So the heat pump will work well and will be the primary source of heat. All right, and ducts. So we talked quite a bit about ducts with all these. Most of these are forced air systems. So forced air meaning that you've got a fan blowing air around the house. And so if you have air blowing around the house, you're going to have ducts to get it there, to distribute it. The ducts are really kind of can make or break the system. You can have a 98% efficient furnace, but if your ducts are leaking into the attic, your 98% efficient furnace can now be 50% efficient because all it's doing is heating or cooling the attic and not the living space. So really, this is one of those homeowners want to change out, want a super efficient furnace, but they don't want to even look at the duct work. They're really hurting themselves because you can't just buy a high efficient furnace and assume you're getting high efficiency into the house. Now, if you're putting that on duct systems that were leaking 30%, and you replace a 75%, right? But ducts are a much cheaper way to make your home energy efficient than it is changing out the furnace or the air conditioner. And yeah, typically ducts, the default leakage rate in California is about 30%. I've certainly seen duct systems that are leaking 90% or more, just disconnected ducts where they've completely come detached. Somebody was in the attic and putting away their Christmas ornaments and stepped on the duct and it fell off or something. So that certainly happens out there. So just don't forget the ducts. It's not all about the expensive equipment, expensive shiny equipment. So not only do you not want them to leak, but you don't want you want them well insulated. And a lot of times you can do a visual inspection and get a good idea. You can also just do a pressure test on the ducts while the blower door is running, and you can get an idea of how leaky they are. But to really know, you need to do a duct leakage test, which is not part of the BPI Building Analyst exam, just a good thing to do on all ducts. And
hey, Scott.
If you're, yeah.
We lost sight of your screen.
Uh-oh.
And I'm trying to hand it back to you.
Okay.
But it's not letting me. If you'd like, I can open it on my computer, and if you want to tell me what you're talking about, or which slide you're on.
Okay. Yeah, why don't you do it on yours, and we'll switch. And you can operate the slideshow. Sorry about that.
No problem.
You still cannot see my screen?
Right.
Okay.
Please, everyone, just oh, it looks like.
Is my screen coming back?
Everybody else can see the screen, so I think you're okay. Let's go ahead and move forward, and maybe it's my computer that's having the problem.
Yeah.
So why don't you go ahead?
I heard the New York Stock Exchange lost their internet today too, so it's not just me, not just us. Okay. So we were on ducts.
You should be good to go. Thanks. Sorry about that.
Oh, that's okay. All right. So here's just some good, the bad, the ugly of ductwork. What you want in ductwork is nice straight runs. It's just you want very little resistance in the flow of air through your ducts. So long straight runs as opposed to the spaghetti that you found down here. This is absolutely crazy. So nice straight runs. You want your corners to be as gentle as possible. So this is not a bad one right here. Let me switch my laser pen. So this isn't bad. I mean, you might even want to angle it in better. This looks like a little bit too sharp. Straight runs. HVAC guys love to hang them from the ceiling. There's some weird thing written in the California code about how they should be attached, which can be interpreted a few different ways. Some building inspectors will not pass you if they're not hanging in the middle of the air in the attic. Talk to your building inspector. Hopefully he'll let you just lay them on the floor of the attic, and then you can put insulation over and around them. It just makes them even more efficient. It keeps more heat in. So ideally you wouldn't have them like this. They would be buried in insulation. And a lot of what I'm talking about with ductwork is pretty California specific. In California we have ducts that are principally found in the attic, which is the hottest part of the house, of course, which is maybe good for heating but lousy for cooling. Where some colder parts of the country don't always have the ducts in the attic like this. They could be in a drop ceiling, which would be ideal, right? Basically, you would have the ducts inside the conditioned space. But leaking is still an issue, even if it's in conditioned space, although it's less of an issue. And then you also, even if they're in conditioned space, how tight the turns are still affect the efficiency of the system. It just gives more resistance. So here's an example of a duct that's either disconnected or at least the insulation is torn on. Ducts can also be metal ducts. These flexible ducts are cheaper, and that's why they're used, easier to install. The metal ductwork probably hasn't been really used for 20 years or so. There's nothing wrong with metal ductwork if it's already there and it's sized properly, and if you can insulate it, even better. So that's the ducts. All right, so just in summary, the main types of heating systems are radiant, which is kind of the gravity wall furnace, natural draft, induced draft, or condensing. Those are the main types. Of course, there's heat pumps and electric resistance heating out there as well. Filters are critical for the operation. You don't want, filters are not meant to eliminate dusting in your house. You still have to do that. That's not the point of them. And just don't forget your ducts when you're thinking about an efficient system in your house. That's a very integral part of keeping the whole system efficient. So we'll talk about a little basic maintenance. Of course, change your filters. I said last time I would usually leave homeowners many filters with dates on them so they know when to change them. But I try to at least do it at the beginning of the heating season and the beginning of the cooling season. You want to check for disconnected ducts. Ducts don't typically become disconnected over time unless somebody or something has stepped on them or chewed a hole in them. But certainly if you're a building analyst looking at a system, you want to look check the whole operation once in a while, at least once a year. Of course, you'll know it when it's not working, but that's the worst day of the year for it not to be working. Typical maintenance for wall furnaces or gravity wall furnaces. You want to clean them every 6 months or at least before the heating season, just to clean the dust off of them. It'll burn off, it's typically, but just to keep it clean. You want to keep the air intake grates clean so that not only combustion air can get in easily and you don't starve the combustion process, but also the heat that you're paying to be created gets out. And part of letting the heat get out is keep furniture away from them. So this is another type of a gravity wall furnace where it's using a fan at the top. That's the fan right here. And this fan is just used to help circulate hot air in the house. So it's just drawing air up over the combustion chamber, which is this, up over and around that, and then blowing it out up here, or it could be set to operate just exactly opposite, where it sucks air in and blows it out down here. Typically it's the former, not the latter. All right, so some other things to check for. Check for flame rollout on startup. If it's been happening, there are usually signs that you will see, and that's what this is here. It's a little sign of flame rollout. That's just where it's been burning the front of the furnace. You want to look, so when you start the burners and you're watching it do its startup, check to see when the blower motor turns on. The blower motor that moves air inside the house should never come in contact with the air inside the heat exchanger. But the way these turn on is the burners kick on and run for maybe 10 seconds before the big blower turns on and moves air around the house. So for those 10 seconds, you'll have a steady flame. When the large blower turns on to move air in the house, at the point that turns on, if you see disruption in your burner flame, that's a sign of a cracked heat exchanger, and so you would want to investigate further. It may not be a cracked heat exchanger, it may be, but it's just one of the visible ways that you can see that there might be an issue. And then, like all the things you do on as a building analyst, you don't want to forget to, a lot of problems you'll either see with your eyes, or you'll hear, or you'll smell. So if you smell here, it smells like a freeway, there's an issue. But if you can smell combustion products, it's an issue. You can also smell gas, right? Natural gas. They put an odorant in it so that you can smell it. So don't ignore your other senses other than your eyes when you're doing an assessment. So this is a natural draft furnace, and so this rust right here, it's not just a bad paint job, but this is from spillage. So when the burner's light and the heat is coming up through the heat exchanger in here, this is where dilution air is added, and then it goes up the exhaust. Well, if the exhaust is cold, or when the exhaust is cold at startup, sometimes exhaust gases can spill out. That's okay, and if it does it for less than 60 seconds. But this is a sign that it's been happening. It's been happening for a while, and it may still pass. It may only spill at the very beginning of startup, but that's what this is a sign of. That rust is from, we talked about condensing furnaces and that the water vapor is corrosive. Well, that's what's happening. If some exhaust gases are spilling out, it gets on this metal, which is, the heaters weren't on, it means it's cold outside. So the metal's cold, just like a can of soda on your desk. So the exhaust gases spill out of here and condense on this part of the furnace, and that condensation, that water is very acidic because of the other products of combustion in it. So just a sign that there could be a problem, a visual sign, check that out. So you would check spillage here on this device. You run a mirror right along this edge here to look for spillage. Spillage is okay up to 60 seconds. At 60 seconds and beyond, it's a failure for BPI. So you can either use a mirror. A mirror is a good indication that it's spilling, or you could use a smoke stick, which is a good indication that it's passing. So use whichever you like, or use both if you're not sure. And a smoke stick, you would run it just underneath the lip. So you want the smoke to have a chance to either be sucked in or to be pushed out. So if it's failing, it would be pushed out. If it's drafting properly, it'll get sucked in. So you want your smoke to just be right underneath, directly below that lip, so it kind of has a choice of which way it's going to go. All right. So you want to observe the operation for a cycle, if you can. Shut down if an issue. Yeah, the modern, anything induced draft furnaces and condensing furnaces, and I'm going to sneeze just a second. Maybe it'll pass. They're complex enough and they have enough electronic sensors on them that they should shut down if there's an issue. They should. Yeah, and just always looking for just visual signs of problems. Some heating systems can have a modulating function, which just means that most of the furnaces in our homes, they're either all the way on or all the way off. They're either 100% on or 0% on. What some newer, more complex systems, they could be modulating. So you can have, maybe 10% of the heat being generated. Uh-oh. Right, can you see me?
Yes, my mistake.
Okay, that's all right. So modulating burners can modulate, or just adjust the amount of heat going in, and so they can, if it's just so that because one of the on forced air heating systems, the longer they run, typically the better, because the blower is going to distribute air throughout the house better. It's going to reduce hot and cold spots. Where if you have an oversized furnace, it turns on, it's on at 100% burn rate. It can heat up the air really quickly, heat up the thermostat really quickly and shut off. It doesn't mean that all the rooms are comfortable at an even temperature. So that's one of the advantages of a modulating system. You can, say, deliver 50% of the maximum heat, and then the system will run longer, and it'll make the home more comfortable. But you don't see them a lot in residential applications, but they're out there. So the basic tools, and we'll look at this more next time. We'll go into some of the CAS testing, because it's just really important for the building analyst to understand gas and combustion appliance safety, CAS, CAS, combustion appliance safety. So the basic tools, you're going to have a gas leak detector. As a BPI analyst, you're required to test all accessible gas lines in a house. So that is basically everything you can get to. If it's in an attic, go in the attic and test it. If it's in a crawl space, go in the crawl space and test it. Obviously, if it's around the furnace or the water heater, test it. Those are all accessible. If there's a gas line running in a wall, it's non-accessible. So when you do find a gas leak with one of these, a gas leak detector, you would want to use some bubble solution. And what that does is it helps verify that there is a leak, because these leak detectors are very, very sensitive and will pick up the smallest, tiniest gas leaks. Many times I'll call a gas service representative out and I know there's a leak there and they won't fix it because it's just too small for them to fix. So a bubble solution not only confirms that it's a gas leak and that it's not a false positive, but it will also give you a relative size. The gas leak detector will, because it'll go off louder and faster typically, but a bubble solution will tell you just how small it is. It's a good indication anyway. And then the combustion gas analyzer, this is a very old type. They don't even sell these anymore, but they all are about the same. And what it does is the cheapest versions will tell you CO, combustion carbon monoxide only, which is that's the carbon monoxide is what will kill you. So that's all they will do. The more expensive ones will give you CO2, will give you oxygen content, will give you combustion efficiency, stack temperature, lots of other data if you should want to use them. So you're going to check for leaks all the time. You're going to check the combustion products on all combustion equipment as well. All right. We got just a couple slides there, and then we'll pause after the controls. So you want to inspect or view one full cycle of operation, start up to, and that doesn't just mean turn it on and listen to it, but actually watch it so you can see the flames. A lot of times you can spot issues with the furnace just visually from like the flame rollout, the issues that I showed you before. But you always want to use a gas leak equipment and combustion analyzers on gas appliances too, to double check them. And then a couple slides on controls. Controls residential wise is just a thermostat, right? Most of the time in homes you're either going to find a bimetal thermostat. A lot of times those are going to have mercury in them or programmable. Pneumatic is larger buildings, commercial or multifamily a lot of times. So bimetal is, what this means is there's two different metals. So on this coil here, there's one type of metal on the inside and a different type of metal on the outside, and they're sandwiched together. So what happens when the temperature changes, the two metals, one will expand at a faster rate than the other one, and because it's coiled and one's growing faster than the other one, it will turn itself. So it's kind of curling itself as temperatures change. So when you talk about bimetal, that's what it's doing. And a lot of bimetals will have like a mercury switch, and that's what this is here. So this little slug of mercury, so now it's showing that it's engaged. Mercury is a metal, so it conducts electricity. One of these wires, there's a wire going in and a wire going out. The metal hits both of these at the same time and turns the furnace on, or the air conditioner on, depending on what it's operating. And as this would cool down, this bulb will flip, so it's kind of at this angle, and the mercury will slide down here and turn it off. That's how the bimetal thermostats work. You want to be really careful with mercury thermostats. There's not, you see fewer and fewer all the time, but that amount of mercury is enough to pollute a very large pond. So they should be disposed of properly. It's a hazardous material and poisonous if it gets in the water system. And so this is a bimetal strip in here. Could be mercury. Yeah, I guess right there's the kind of the tip of the mercury bulb. So it's a mercury in there too. It could be a square one too, but just showing the round one. And then programmable, I think everybody knows what programmable thermostats look like. There's tons of them out there, ranging from $10 to at least $200 or $300. For fancy ones, programmable thermostats work really well if you program them, of course. And also, from your BPI analyst, if you're doing a test, every thermostat works differently. Programmable thermostats are not always straightforward, so it's a good idea before you take a field test to make sure you know how to operate the thermostat. I say that all the time, and people say, yeah, I know how to turn it on and off, and during the test they can't turn the furnace on, and I can't help them while they're testing. So just know how to do it. And then here's a picture of a pneumatic thermostat. Keep moving here. But we'll pause here before we go into DHW, domestic hot water, for any questions, Mike.
Perfect. Do heat pumps work better in conjunction with geothermal, such as if the refrigerant is preheated or pre-cooled?
They can, yeah. Preheating or pre-cooling the refrigerant can work. A lot of times the geothermal systems are using water. You're preheating or pre-cooling the water with the earth, and then the heat pump, instead of taking heat out of the air, it takes the heat out of the water that you're in the geosystem. So what it does is it'll allow a heat pump to operate at, when the outside air temperature is much lower without the electric system's backup.
And the next question, is there a way to reseal metal ducts that are already inside a house without having to take apart the walls?
There is. It's the brand name is AeroSeal. AeroSeal. You can look it up on Google. I think that's just a brand name. There's probably other types out there, but they just run a little probe through the duct work. So they pressurize the duct. It's like to fix a flat for your car. So they pressurize it. They shoot some of the material inside the ducts, and it tries to leak out. And as it's leaking out, it seals the holes. So it works just like a fix-a-flat on your car would. It won't fix humongous holes in ductwork, but it fixes, I don't know exactly the specs of how big a hole it'll fix, but it's not going to fix a disconnected duct or a 4-inch hole in a duct, but it'll fix a lot of leaky ducts without taking them apart or taking walls apart.
Okay, and those are all the questions now, so let's go ahead and move on.
Okay, great. DHW will spend the next 20 minutes on water heating. Just a little good information, just California, just relative size of the whole market, not just about water heating, but there's a lot of buildings out there to get to, 13.4 million in the state. And here's it's a few years old from Energy Star, but water heating makes up 13% of that energy use in the house, so it is the second largest after heating and cooling, and should not be ignored. It's usually a lot of the fixes for water heating or improvements, energy improvements in water heating are really simple and really cheap. And it's the second largest, so just don't ignore it. Domestic hot water, DHW, is how it's often referred. So defined as it's water used in a building for domestic purposes. So that's drinking, bathing, and washing dishes and washing clothes. So if you're talking about DHW, it does not include space heating. Like we talked about hydronic space heating, so it's just a way, the nomenclature to distinguish it from like basically water that you're going to come in contact with. Some relative importance here in just where water is used, hot water is used in the house. We'll do like household use per day. So a bath is 11 gallons, clothes washing is 10, dishwasher 2, faucets 22, and the other big one's showers. So, you know, there's a lot of great technology in dishwashing right now that can really improve upon the reduce the amount of hot water used, but in general, it's a pretty small one to go after anyway, just a couple gallons a day. Where your clothes washer, you have a much larger impact. My team and I, we've been talking about this, and there's very few reasons why you would ever need to wash clothes in hot water today. That was something that was done in the old days. Your grandparents did it. They didn't have good soaps. Now the technology of the soap is such that you should almost never need to use hot water. And as a person who doesn't like to do laundry and sorting clothes, that's great, because that means you can throw it all in one wash and wash clothes. You don't have to sort things anymore if you run them all in cold. So I think this one can be pretty much eliminated completely if people understand that hot water is just not necessary for clothes washing anymore. If you need to sanitize them, bed bugs or lice or something, that's different. And this is a really hard one to get people to stop using hot water. But I've done it for years. It's just not necessary. The other big one is faucets, and that can be fixed just by $3 aerators on your faucets. Typical 2.5 gallons per minute is the maximum allowable in the state of California, but a lot of commercial restrooms in particular have 0.5 gallons per minute faucets. For $3 you can buy an aerator, screw it on a normal faucet, and you can cut your hot water use dramatically. I would also argue, and I try to convince my family, that they don't need to use hot water in a faucet typically. If you're washing your hands, it's just by the time hot water got to the faucet, I would already be done washing my hands. So all I would be doing was using hot water I'd be filling up the pipe with hot water. I actually wouldn't be using it. So just wash your hands in cold water. And showers is just what you've got to do. But we'll talk about that a little more. There's also the demographic characteristics of hot water use, and some of these are obvious, right? If there's a high percentage of children in the home, you're going to use more hot water, washing diapers and stuff, right? But it has shown, the data shows that like low income use more hot water than middle income down here is using little amounts of hot water for various reasons. Seniors use very little hot water. So this is something also to be considered when you're looking at a home and how people use hot water, is the demographic characteristics. So it's not only where they use water, showers or dishwashers, but also the demographics. And here's a couple years of gas data from a home in Sacramento. This family had there's a husband and wife and 4 kids in the house. So certainly, a lot of people in the house. And I'll explain this a little bit. So this is cooling degree days. So this is, we talked about it before, how hot it is outside, right? And then heating degree days is this line here. So that's how cold it is outside. So the gas usage increased the colder it got outside. It pretty much mirrors the temperature outside really well in that winter and this winter. And then these are the summers, because it's hot outside, right? So these are the summers. So what this is showing is the base gas use is about right here, right? So when you chart utility data, it's really interesting to pull it out, right? So here, this home is using about $9 per month of gas. So that's on their base usage, and so that's primarily 6 people is primarily going to be used in showers. Of course, there's going to be a dishwasher in there that's using hot water, and it's also going to be cooking. There was also gas cooking. So for about $9 a month, they were cooking, washing dishes, and no, they weren't washing laundry in hot, and they were bathing. So $9 a month, and that's nothing special in this house. It was a subdivision build out in 2000, I think about 5. So it's a newer home, standard tank water heater, maybe at best 62% efficient. So this is what's possible with just behavior, basically. $9 a month. So, but kind of the summary is there's a lot of opportunities, and base load reduction is what you're working on with your water heating. So it's good because it's every month of the year, unlike heating. So there's different types of water heating. There's tank and tankless, indirect. I meant to take lead lag controllers out. Expansion tanks and circulation pumps we'll talk about. So the types, the tank type, we'll get into instantaneous or tankless and indirect. So this picture here is of a tankless unit that's installed in a home somewhere. And we'll talk more about them. So boilers versus water heater warrants at least a slide. The way we define it in California is a boiler has greater than 75,000 BTUs per hour of input, and water heaters have less than 75,000 BTUs per hour of input, and typically less than 140 degrees. Where boilers are larger, they're more than 75,000 BTUs and can be much hotter. It's just a pretty picture on the right of the flames heating water in a water heater, but there is a difference, and really it's about size. What throws people off, and I think we've spoke about it on this call before, is that a lot of times water heaters, like instantaneous water heaters, can be 200,000 BTUs per hour, but they're still classified as a water heater and not a boiler. I think the distinction is just because they do not have a tank. There's no tank. There's no water sitting there. So we'll start on water heaters. We'll start with the highly efficient, the greater than 90% efficient. You've got condensing, this is a condensing propane water heater. The A.O. Smith brand makes several good condensing ones that I've installed a lot of. These are also can go up 100,000 BTUs. Is probably a small one. They're condensing, but they're also modulating, so they would have like maybe a minimum BTU per hour input of 20,000, maximum of 100,000 or 200,000 BTUs, depending on demand from the water system. They are power vented. You've got the same thing as your furnaces, where you've got the PVC pipes here as your exhaust, because you've taken all the heat out of the exhaust, so the exhaust temperature is very low, and the other one's going to be your air input, your combustion air going into the system. And also, speaking about efficient, just an electric resistance water heater is, again, it's about 90% efficient, or nearing 100% efficient, 92 to 98% efficient, but the cost of electricity is much greater. So on this, on this electric resistance, there's two heating elements. There's one here and one here in the tank, but they are efficient. They're just expensive to operate. And then so some other electric water heaters. So again, electric resistance, somewhere around 95% efficient. They're not practical for a central system. This is kind of meant in multifamily. You're not going to have a central electric water heating system. They do recover more slowly. That means if you take a lot of showers, it's going to heat the water up more slowly. And then there's heat pump water heaters, which is what this one is on the right. They operate just like a heat pump does to heating or cooling your home, except it heats the water. They're going to be 200% efficient or better. They do heat water even more slowly. So one of the downsides of a heat pump water heater is usually you need to have a larger tank because it cannot recover as quick when you're taking showers. But the big advantage of these is that it's going to get rid of yet another combustion product from your house. The cost of these, something like this, is probably at least around $1,500. If you're a builder and it's building 200 homes, you could maybe take a third off of that. But if you're going to install one of these in your home, I just priced one last couple of days for $1,300. There was can't remember who made it, but A.O. Smith maybe. Condensing, not condensing, excuse me, a heat pump water heater. Great when you have solar electricity and so your electric is already covered. And then it's kind of mid-efficiency water tank water heaters. There's not many smaller residential mid-efficiency water heaters out here. So the ones that I'm showing you here are larger, probably are going into the boiler size, so above 75,000 BTUs. But those can be usually 75 to 80% efficient is probably a better range. But they can be power vented, and they're oftentimes are going to have a damper. So that's what this is right here. This is a damper, and this is the motor for the damper. So here, when the damper's open like this, it should be firing, so it's heating the water. So when it's off and you're no longer firing, the damper closes, and it just helps seal in the air, so it stays more efficient. The burners are down here, and typically these are going to be electric ignition, where most residential water heaters have a standing pilot. Standing pilot just typically is going to be wasting electricity. Ooh, and I'm about out of time. Got a boogie. So lower efficient, I am out of time. Lower efficiency ones are the more standard. Natural draft, they're going to be open combustion and standing pilot, like I just said. And then there's the tankless or instantaneous. They're starting at 82% efficient and can go up to the 98% efficient. One of the big advantages of these is not in saving energy, but it's being able to place it like outside the building. So you get combustion outside the building, plus you free up storage areas inside the house. But they do not, a lot of times they do not save energy, even though they're more efficient. People just use them more. Nothing like running out of hot water to save energy. And then there's indirect water heaters. This is in a residential application. This is really going to be used more when there's a solar system, a solar water heating system on the house. So we'll kind of go through that one, but there's no combustion in that system. It doesn't have to be. And then there's expansion tanks that just keep how this works. Is there's a expansion tank is here. There's air in half of it. When the water heats, it expands. What you don't want it to do is push the hot water back down the cold water pipe. So that's what your expansion tank is for. It can absorb the increased pressure there. And then recirculation pumps. So these are little pumps that move the water around the house continuously. They can be continuous, or they can be on a timer or temperature sensor. They reduce wasted water while you're waiting for your water to warm up, but they do increase energy use because the pump that recirculates the water is electricity, plus you've just got pipes full of hot water in the house that are going to cool down and lose energy. But they can save water. So just a couple more slides here. Good insulation, bad insulation. This is a draft hood. Hot gases can and will spill out. You need proper clearance, 6 inches to single wall, and usually an inch, 4 inches to 6 inches to single wall, 1 inch to double wall exhaust pipes. This may even be too close, but they at least did a good job. You want to insulate the hot and cold water pipes because hot water rises just like hot air. So if I think this is the cold water pipe, so hot water is at least going to rise up to here. So insulating that's going to save a little bit too. And water temperature. Of course, the lower the water temperature that sits in the tank, the less energy you're gonna use. And there are ingenious ways to recover waste heat from your shower. That's what this is doing. It's recovering heat from your hot shower water. We won't go into it because we're out of time. Routine maintenance. Lower flow fixtures, you can always go lower. Even if you've got the law is 2.5 and you've got a 2, you can always go to 1.5 or 1. You can always go lower. And a lot of this is keep things clean, keep things out of the area of the water heater, and make sure you've got enough air to combust properly. Aerators. So this is the aerator. This is a little thing that screws on the end of your faucet. You can get lower flow aerators for $3 to $5, save a lot of water. Toilets don't use hot water, but they save water anyway. And then Energy Star appliances. Always go on the Energy Star website. Just because it's Energy Star doesn't mean they're equal. There's tiers of Energy Star that you always want to look through. And just like furnaces, air conditioning, water heaters, you also want to size properly. You only get one chance to do it right, so do it. And sorry I rushed that last section, but I wanted to finish up. Any last questions, Mike?
We haven't gotten any new questions by text, but there's quite a few people who have asked questions throughout the presentation, so just want to open it up to anybody who's interested in asking a question on any of the sections that happened so far today. Please feel free to speak up. While I'm waiting for questions to come in, I again want to reiterate that this recording will be available to you on YouTube shortly, and you're going to receive a link to a survey requesting some feedback from all of you at the end of this presentation. So please send us your feedback about the content of the presentation and the quality of the presentation, as well as if you're interested in applying for or getting credit for continuing education units through BPI. This course will qualify for that, so please send us your BPI certification number if you are interested in that. This would of course only apply to people who are already registered BPI practitioners and have a BPI certification number. Got one question that came in while I was finishing up there. How can you determine the size needed for a water tank?
Great question, and they're basically by use. The only way I've searched through the literature, and most of what I've seen, it's for new construction. But if you've got an existing building and you can measure water use or gas use of the water heater, you can then adjust. I've done this kind of study on multifamily buildings before and been able to dramatically reduce the size and therefore the expense of the water heating system going in. But the smaller system that goes in, the less standby loss you're going to have also. So there's not only is there you reduce the cost going in, but you're going to reduce the operating expenses. But harder to do on residential because there's not very many options there. Great.
Well, I think that is the last question. So if there are any other questions on the line, please feel free to email one of us. You see both of our contact information posted on the screen right now. Any questions related to the program or policies specific to the program, feel free to direct them at me. Any questions related to BPI testing, BPI practice, textbooks, equipment, please direct those to Scott, and his contact information is on the screen there. Thank you for the information today, Scott. We covered a lot of topics, and that was pretty chock full of good information. So I will leave the last word to you, and once you're done, I will stop the recording and close the meeting for everybody. Thank you all for attending.
Thanks, Mike. Yeah, the only thing I'll leave you with is if you signed up, we will be emailing you like a flyer that will talk more about study materials, what study materials you can do on the side, give you some of those, names of those, and it will give you more information about the on-site classrooms that will be happening toward the end of August and how to sign up for those. So that will be emailed out to you shortly. You should get it by the end of the week, I would assume. So that's all I got, Mike. Thanks a lot, everyone.